Hello, in this video I'd like to talk about pure iteration. I'll be heavily restricting our construction of the primitive recursive functions, but without losing any expressiveness. Every primitive recursive function can be given by pure iteration. This video is almost exclusively based on Gladstone's 1971 paper, Simplifications of the Recursion Scheme. This is the fourth video in my series on primitive recursive functions. I'll try to make it as self-contained as possible, but I encourage you to go back and watch the other videos in this series to get some context for why we care about primitive recursive functions and what we can and can't do with them. I want to talk about a restricted form of presentation for the primitive recursive functions. I'll say that a function is pure iterative if it is, just as before, a constant function, the successor function, or a projection function, or a multivariable composition of functions that we've already established as pure iterative. Or a pure iteration. If we already have pure iterative functions g and h, we can construct a new pure iterative function f, where f of 0y is g of y, and f of x plus 1y is h of f of xy. Notice that we've lost quite a bit here. I've written out the definition of primitive recursion here so that you can see all that we've lost in this definition. H no longer gets access to x. If we're thinking about this in terms of for loops, this is like not having access to the index variable I. H also doesn't get direct access to y. The only time we're allowed to access the other input to the function is in the base case, where the first argument is 0. And I've also removed the ability to have lots of variables as input to our pure iterations, lots of different y's. Technically, we still call it pure iteration, even if we do have arbitrarily many variables. This here is called pure iteration with one parameter, the y's being the parameters. Either way, it doesn't matter. We'll still be able to use some sort of pairing construction and multivariable composition to get back the ability to talk about functions of arbitrary arity. And that's the main goal here. Once we show that we can do some kind of pairing operation, some way of encoding multiple natural numbers as a single natural number, and then being able to extract them again, it'll be easy to recover all of the features that we lost from full primitive recursion. The challenge is going to be being able to construct a pairing function with such limited tools. And that's going to be pretty tricky. In the first video in this series, I showed you how we can create a pairing and unpairing function using the full power of primitive recursion, and we genuinely made use of some of the features that we no longer have access to in the pure iterative functions. The challenge is, can we construct those pairing and unpairing functions using this much more limited definition? Let's go through the proof that we haven't lost any expressiveness when limiting ourselves to pure iteration. That is, the pure iterative functions and the primitive recursive functions are the same. We start by noting that our is0 and an is non-zero function, which returns a 1 if the number is non-zero and 0 if it's 0, are pure iterative. The construction uses constant functions and doesn't make use of anything in the recursive case. And this is important to Boolean logic because the is0 function acts as a negation on Booleans. Right? Remember that we're considering 0 to represent false and 1 to represent true, and of course asking if a number is 0, asking if a Boolean is false, is the same as negating it. We can also do addition. You can just check that our construction of addition didn't make use of anything beyond pure iteration. And we can use this to implement Boolean OR. And of course, not A or not B is the same as A and B, so we can do Boolean AND. If we introduce a temporary helper function h with h of 0y equal to y and h of x plus 1y equal to 0, again it's a similar constant function trick, then we can define the ternary operation as a sum of h terms. This is the question mark colon operation from C-like languages. The function is y if x is 1 and z if x is 0. Only one of our summands will be non-zero. If x is 0, the first term will be z, and if x is 1, then the second term will be y. And from the ternary, we can construct any piecewise construction we want, as long as we've already shown that the outputs and conditions are pure iterative. So we haven't really lost anything in terms of logic and our ability to do piecewise constructions. For this proof, we're going to use another one of the standard pairing functions. This is very nice. It's a way of encoding a whole bunch of natural numbers, potentially, as a single natural number, using the exponents in a prime factorization. We're going to encode the pair xy as 2 to the x times 3 to the y. So to get started with that, we're going to need to show that exponentiation, at least with a constant base, is pure iterative. First, note that since addition is pure iterative, multiplication by a fixed constant is pure iterative, since it's just a multivariable composition of a bunch of addition. We can't directly use our multiplication function. If you look back at the proof in video 1 that multiplication is primitive recursive, I made use of some of the added functionality of primitive recursion that we don't have with pure iteration. But multiplication by a fixed constant is perfectly fine. And we can use that multiplication by, let's say, 5 is pure iterative to show that the function h of xy equals 5 to the x times y is pure iterative, given by h of 0 y equals y and h of x plus 1 y is equal to 5 times h of xy. And then we can do multivariable compositions of these sorts of functions to construct whatever exponential functions with fixed bases that we want. But that's the easy part, encoding our tuples. What about decoding them? How can we extract x from 2 to the x times 3 to the y? That's going to be quite a bit trickier. Gladstone's proof goes through the process of showing that one useful function after another is pure iterative until we get the unpairing functions we're looking for. Showing that we can do modular arithmetic using pure iteration is quite a slog. We're going to have to work our way up, function by function, showing that we can recognize numbers with particular remainders and check if a number is equal to a fixed constant, starting at very small numbers and working our way up to larger and larger numbers in an inductive fashion. Remember that we don't even have a function that tells us if two numbers are equal yet. So even though we're allowed in kind of the basic pure iterative functions, functions that can output arbitrary constants, we can't yet compare against those constants. Again, this is a proof by induction, and here's the base case. If we look back at our function isOdd, we can define it pure iteratively like this. Next, let's define a temporary function f using this pure iteration. F of 0 equals 0, and f of x plus 1 will be f of x plus 1 if f of x is 0 and 2 otherwise. Remember that we can do piecewise definitions using our ternary function and are given direct access to constant functions. We do, however, need to be careful that when defining these piecewise functions to apply to f of x, we're only referring to f of x. Remember that in our definition of pure iteration, we're only allowed to determine f of x plus 1 from f of x. We're not allowed access to x. The sequence of values of this function f goes 0, 1, 2, 2, 2, 2, 2, and so on and so forth. So we can tell if a number is 1 by asking if f of x is odd. So that's our base case. Now let me show you the next step in the induction, using these functions to define the mod3 function and the isThisNumber2 function. It'll be really convenient to have a function that tells us if a number is at least 2, which we get by composition of previous functions. A number is at least 2 if it is not 0 and not 1. And we've already shown that the is0 and is1 functions are pure iterative. This is really clever. It gets us partial access to the number 2, even though we don't yet have a function that exactly tells us if the input is 2, an is2 function. we can use our isAtLeast2 function to define a function that gives us the remainder modulo 3. Of course, mod 3 of 0 is 0, and then mod 3 of x plus 1, well, that's usually going to be mod 3 of x plus 1, unless mod 3 of x is 2, which we can tell by using our atLeast2 function. And then we define a temporary function f, similar to the one in the previous slide, with f of 0 equal to 0, and f of x plus 1 usually given by f of x plus 1, unless f of x is at least 2, in which case we output the constant 3. The sequence of values of this function looks like 0, 1, 2, 3, 3, 3, 3, 3, and so on and so forth. And then we can define the is2 function that just checks if the remainder of f of x is at least 2 modulo 3. And then we can keep doing this to define the at least 3, mod 4, and is3 functions, and then the at least 4, mod 5, and is4 functions, and so on and so forth. We still can't put a variable in any of these subscripts, but at least we have the ability to do whatever modular arithmetic we want, modulo concrete moduli. So we could ask if the remainder mod 10 of a number was equal to 5, for instance, and get a function that outputs 1 in those cases and 0 otherwise. I want to show you how we can use our modular arithmetic to define a function that roughly multiplies by 13/5, specifically that multiplies by 13/5 and then rounds down. Here I have a table of values of 13/5 x. And then by removing the decimal parts, we get a table of values of the function f. If we look at the remainders of these values, modulo 13, we get a pattern that repeats with period 5. And we can use this pattern to define f as a pure iterative function. F of 0 is, of course, 0. And then we want to go from one value of f in the table to the next. And to do this, we wind up either having to add 2 or 3, 13/5 rounded up and 13/5 rounded down. And which one we add is always the same depending on where we are in the cycle. So to define f of x plus 1 in terms of f of x, we first look at the remainder of f of x modulo 13, and that tells us where we are in the cycle, and then add the appropriate value using our conditionals. Again, we have to go through this extra work here because we can only define f of x plus 1 in terms of f of x. We're not allowed access to x in our definition. Note that this construction only works for fractions larger than 1. If we tried multiplying by, say, 2/5 and rounding down, we'd get successive values of f of x that were equal to each other. So we couldn't determine f of x plus 1 just by looking at f of x at all, let alone just using pure iterative functions. But otherwise, this sort of construction here works for any fraction we like. If you've seen my video on Fractran, perhaps you can see where this is going. We would like to be able to operate on the exponents of a number, written out in terms of its prime factorization. Right? We had the number 2 to the x, 3 to the y, and we wanted to be able to extract x from that. And the way to do that is with an operation that multiplies by a fraction until it can't, until doing so would leave us with a number that wasn't a natural number. We'll call this function m sub that fraction. So for example, to calculate m sub 2/3 of 90, we can multiply 90 by 2/3 once to get 60, and then again to get 40. And then we can't multiply by 2/3 again without getting a fraction, so this is the output of the function. Of course, if we can't multiply by 2/3 at all, then we just output the number that was input. In general, if we input a number of the form 2 to the a, 3 to the b, 5 to the c, we'll be able to multiply by 2/3 exactly b times before all the 3's are gone, and doing so we'll multiply by 2 to the b, so we're effectively moving the b from the exponent of the 3 to the exponent of the 2. To implement this function, let's build an intermediate function f of xy that applies this multiplication by p over q to y at most x times. Of course, if x is 0, we don't do anything. We just output y itself. On the other hand, for x plus 1, we look at f of xy and then apply our multiply by p over q and round down function if q divides f of xy. If we can multiply by another p over q because there's a factor of q in there, then we do so. In this case, there won't actually be any rounding down, right? We said that f of xy was divisible by q. And don't forget that we can tell if q divides f of xy by checking if f of xy is congruent to 0 modulo q. Q here is a concrete number. And then, of course, if q does not divide f of xy, we've multiplied by p over q as much as we can, so we don't do anything. So, how many times can we multiply y by p over q? Well, once for every power of q in y. This number is very small, but since we assume q is at least 2, it definitely has to be less than y. This is probably overkill. So, calculating f of y will multiply y by p over q a sufficient number of times. So it'll give us m sub p over q of y. And again, we can only do this argument if we already have the function that multiplies by p over q and rounds down. So only when p over q is larger than 1. Our m sub 2/3 example from above we'll have to wait for later. Here I'm going to diverge from Gladstone a bit. It's always fun practicing a bit of Fractran-style programming. Of course, we don't have the full power of Fractran. Fractran is Turing complete, while the best that we can hope for is that our pure iterative functions are as powerful as primitive recursive functions. Suppose we have two values, x and y, and we want to compare them. First, we can calculate 2 to the x, 3 to the y, and then multiply by 7/6 until we can't. If x equals y, we're multiplying 6 to the x by 7/6 until we can't. The result will be 7 to the x. If x is less than y, we can multiply by 7/6 x times. This will get rid of all x of the 2 factors and x of the 3's and give us instead x 7's. This resulting value is odd, so we definitely can't multiply by 7/6 again. If x is greater than y, the reverse happens. We can multiply by 7/6 y times, getting rid of the 3's and y of the 2's, and giving us y 7's instead. The result isn't divisible by 3, so we can't multiply by 7/6 again. So now, by detecting which of these cases we fall into, we can determine how x and y compare. If this number we get is divisible by 3, we fall into the second case, so x is less than y. If this number is divisible by 2, we fall into the third case, so x is greater than y. And otherwise, x is equal to y. So this is great. We finally have predicates to determine if two values are equal or satisfy various inequalities. So back to Gladstone's proof, suppose that we have some number whose prime factorization contains 3 to the a, 5 to the b, 7 to the c. If we apply m sub 11/3, 13/7, and 13/5, it will turn the 3's into 11's and 5's and 7's each into 13's. The result will have 11 to the a and 13 to the b plus c in place of those original factors. If we do the reverse, if we turn the 3's into 13's and the 5's and 7's into 11's, the result will have 11 to the b plus c and 13 to the a in place of those original factors. These will be equal if and only if a is equal to b plus c, if the number of factors of 3 is the sum of the number of factors of 5 and 7. So by taking these compositions of m functions and composing them with our is-equal function, we can create a pure iterative function g, which takes in a number and tells us if the number of factors of 3 is the sum of the number of factors of 5 and 7. This g function isn't of much interest on its own, but it will allow us to recognize numbers of the form 2 to the z plus z, thus connecting powers of 2 and their exponents, stepping us along the way to being able to take logs base 2. Let's construct, using pure iteration, the function f of xy, with f of 0y being 3 to the y times 5, and f of x plus 1y usually getting its value from f of xy by applying a series of m functions and multiplying by 7, until we reach a value where the exponent of 3 is the sum of the exponents of 5 and 7 in the prime factorization, right? Until we get a value that satisfies this g predicate, when we crash the value down to 0 and it'll stay there. Our series of m functions here do a clever thing. They turn all of the factors of 5 in an input into 11s, right? M sub 11/5 of 5 to the x is 11 to the x, and then turn those factors back into 5s, but twice as many 5s. So every time we go around our loop, the exponent of 5 in our prime factorization will double, and by multiplying by 7, we'll add 1 to the exponent of 7 as well. So let's say, for instance, we start off with y equal to 11, which is a number of the form 2 to the z plus z for z equal to 3, and we look at successive values of our function f. We'll start off as specified with 3 to the y times 5. The exponent of 3 is not the sum of the exponents of 5 and 7. 11 is not 1 plus 0, so we'll take a step forward, doubling the exponent of 5 and adding 1 to the exponent of 7. Again, we still don't satisfy our g predicate. 11 is not 2 plus 1, so we take another step forward, doubling the exponent of 5 and adding 1 to the exponent of 7 to get f of 211. 11 again is not 4 plus 2, so we take another step forward, doubling the exponent of 5 and adding 1 to the exponent of 7. Each time we do this, the exponent of 5 is always going to be 2 to the power of the exponent of 7. And now we do satisfy the g predicate. 11 is 8 plus 3, so we crash down to 0, and we stay there every further time that we increment x. So a few things to note here. The exponent of 3 started at 11 and stayed at 11, and we only crashed down to 0 because some pair of z and 2 to the z, the exponents of 7 and 5 respectively, gave us a sum of 11, satisfied the g predicate. If we started with some other y that wasn't a sum of some pair z and 2 to the z, we'd keep stepping forward and never crash down to 0. The other thing to note is that this happened going from the third step to the fourth step, that is, coming out of the z step, where z is such that 11 was 2 to the z plus z. If we have some y, in this case 11, and are looking for some z such that 2 to the z plus z is equal to y, then we're not going to have to look that far. In particular, if we don't crash down to 0 by the yth step, we're not going to crash down to 0 at all. So if we plug in y for the first coordinate, that's going to tell us if y is some sum of 2 to the z plus z. If it is, as we increase the first input from 0 to y, we're going to crash down to 0 and stay there. And if it's not, as we increase the first input from 0 to y, we're never going to crash down to 0. So by composing this f function that we've created here with pure iteration, with our is this number 0 function, we have a predicate now, a pure iterative predicate that recognizes when a number is of the form 2 to the z plus z. One of the real key functions when working with primitive recursive functions is the predecessor function. There's a previous paper by Robinson that identified the predecessor function as a key step of this proof that hadn't been completed yet. Gladstone handles the case where we want to take the predecessor of even and odd numbers separately, so let's start with the even numbers. The paper defines this intermediate function f, given by f of 0y is equal to 2 to the y, again we can do that, and f of x plus 1y, usually adding 2 each time we increase the first argument, except when we reach an even number of the form 2 to the z plus z, when we reset down to 1. Let me walk through a basic sequence of inputs for this function. Suppose that we start with y is equal to 4. then f of 0y is going to be 2 to the 4th, or 16 by definition. And then we go through progressively adding 2 each time until we reach a number of the form 2 to the z plus z. The next number of this form after 2 to the y is always going to be just 2 to the y plus y. And since we've been adding 2, the result is even. So at the next step, we reset to 1. Note here that we've reached another number of the form 2 to the z plus z. But since this is odd, it doesn't activate the reset again. And that's part of the clever bit here. And then we add another 2 to get 3, the predecessor of 4. The idea is that f of y is going to give us the predecessor of y for any even y. I guess greater than 0. In general, the sequence of values is going to follow this pattern here on the right, starting at 2 to the y, working up in steps of 2 until we get to 2 to the y plus y, then resetting to 1 and working our way back up, ultimately to y minus 1. I've written the entries of this table in this particular way so that you can see that these numbers and these numbers are the same on the journey back up from the reset. And it's at this resetting that the clever bit happens. When we reset to 1, we're technically on the first step of the second part of the journey in steps of 2. So if we were hoping to get back to where we started, we would actually need to be at 2. We're 1 short, and that's exactly the 1 that we're subtracting in our predecessor function. Now on our journey back up, we're going to be passing through all the odd numbers from 1 to the predecessor we're looking for, and that's going to pass through a number of values of the form 2 to the z plus z. 1 is of that form, 3 is of that form, 11 is going to be in that form, but since we're only passing through odd values, none of these is going to catch on our conditional and accidentally cause another reset to 1. So for y even, f of y is the predecessor we're looking for. On the other hand, if y is odd, we're going to get complete garbage data. 2 to the y plus y is odd, and so we're never going to catch on it. We're actually going to catch on 2 to the y plus 1 plus y plus 1. And actually, we're also going to get garbage data when y is equal to 0. F of 0, 0 is actually 1, and we'd like it to be 0. The predecessor of 0 is defined, because it can't be negative, it's defined to be 0. But this is an easy fix with our is0 function and piecewise constructions. If y is odd, we can use a very similar construction. We just have to fiddle with the parities of things a bit. Feel free to pause the video to get a sense of how this construction works. So again, we can define our predecessor function piecewise, handling separately the cases where x is 0, x is even and greater than 0, and x is odd. And we can now, as we did before, define subtraction. But of course, all of the functions I've been talking about only work with natural numbers, so of course we have to work with bonus, subtraction, but return 0 if the difference is negative. We start by defining the function that does this backwards. Sunom of xy is going to be y minus x clamped to be positive. This is just the definition from the first video in the series. Sunom of 0y is equal to y, and sunom of x plus 1y is going to be the predecessor of sunom of xy. And then we just define bonus by reversing the arguments to the function using our multivariable composition and projection functions. Remember that our ultimate goal was to construct pairing and unpairing functions. And to do that, we plan on encoding numbers in the exponents of a prime factorization. And in order for that to work, we need to be able to get numbers back out of those exponents. That is, take logarithms. Define the temporary function with f of 0y equal to y, and increasing the first argument by 1 increases the output of the function until we hit a number of the form 2 to the z plus z. Now, on any inputs, if we step forward long enough, we'll eventually get to a number of the form 2 to the z plus z. The second input tells us what number to start at, and the first input tells us how many steps to take. So if we start at x and take 2 to the x steps, we'll definitely wind up at a number of the form 2 to the z plus z at some point. In the worst case, I mean, x plus 2 to the x is of that form, but that's way larger than it has to be. So f of 2 to the xx rounds x up to the next number of the form 2 to the z plus z. So if we knew that x was of the form 2 to the y, then we can extract y, just by rounding up to the next number of the form 2 to the z plus z. And that's specifically going to be 2 to the y plus y. And then if we subtract our x, if we subtract our 2 to the y, we're just going to be left with y. So again, round up and subtract x. Here I'm using a minus sign with a dot over it for the minus operation. This is standard notation. It won't be important what this function gives us for other values. If we input a power of 2, this function here will calculate the log base 2. So we're finally here. Using subtraction, we can create any multiply by a fraction and round down function we want. For instance, multiply by 2/3 and round down is just multiply by 5/3 and round down, and then subtract x. This allows us to create arbitrary multiply by p over q until you can't functions. Recall that we decided to encode the pair of numbers xy as 2 to the x times 3 to the y. Then to get the left value, we multiply by 1/3 until we can't to get rid of all of the 3's. And we're just left with 2 to the x, and so if we take the log base 2 of that, we'll get our original x. And to get the right value, to get y, we multiply by 1/2 until we can't to get 3 to the y, then multiply by 2/3 until we can't to turn that 3 to the y into a 2 to the y, and then take the log base 2 of that to get our original y. And this construction here doesn't just allow you to encode pairs of numbers, but actually arbitrary tuples of some fixed length directly in the exponents of the prime factorization. So we don't need to do any nonsense with nested composition of the pairing function. Now that we've shown that we can encode and decode arbitrary tuples of natural numbers using pure iterative functions, we're ready to show that any primitive recursive function can be created using pure iteration instead. Recall the differences. With primitive recursion, I'm allowing more than one extra parameter, more than one y, and the function h that updates the value of f from one value of x to the next has access to x, the previous value of f, and the extra parameters y1 through yk, while with pure iteration, the h function only has access to the previous value of f. So the solution is simple. We're going to encode in the output of our function f not just the value that we want, but also all the other data that h needs. So when we feed the previous value of f into h, it can decode that data and use it as necessary. The precise construction looks something like this. The starting value of capital F is given by tupling the starting value of x, the starting value of lowercase f, and the starting values of the other parameters y1 through yk. Then on the update step, we're updating all of these values, adding 1 to the first value, updating the value of lowercase f by running all the data h needs through h, and then the values of y1 through yk don't update at all. Perhaps it would be easier to see this with a specific example. Let's consider the basic primitive recursive function that calculates the nth triangle number. Note that this definition here is not pure iterative. The update function needs access to not just the previous value of try, but also access to x, and pure iteration doesn't allow that. So let's construct a function f by pure iteration that keeps track of the pair of x and the xth triangle number. It starts off at the pair 0, 0, and each time we want to update our pair, we add 1 to the left value, we add 1 to x, and then we update the right value, the triangle number, by adding our x plus 1 plus the previous triangle number we were keeping track of. Right, we'll start off at 2 to the 0, 3 to the 0, saying that x is 0 and the xth triangle number is 0. And then we update by adding 1 to the left value and 0 plus 1 to the right value. And then we update again by adding 1 to the left value, and now 1 plus 1 to the right value. And we just keep doing this until we get to the desired x. And then the x triangle number is just the right value, the power of 3 in f of x. And the process of keeping track of other data from step to step of our pure iteration is exactly the same. If there's some fixed parameter y we need to keep track of, just keep track of it in a pair in the same way, just don't add 1 each step, keep the value the same. So thanks for joining me on this windy journey to show that all primitive recursive functions are pure iterative and this whole primitive recursive march. I'll have another video for you next week, but in the meantime, please leave any questions or comments down below and be kind to each other.